Okay, so today we are going to be continuing on in Module 6. So as we look at our learning plan here, we are going to be looking at example number 2. The last time we were together, we had example number 1. Example number 2 is going to be similar, but a little bit more variety on the machine elements on the shaft. Last time we only had gears on our shaft. This time we're actually going to have V-belt drive or a V-belt sheave, chain sprocket, and a gear on one shaft. So we'll kind of see a variety of different elements and how to handle those. I'm not going to pull up the PowerPoint presentation just right now because I'm going to kind of work out of our book and underneath here rather than trying to flip between, but we will be referencing MD solids and pulling that up and going through that process and getting you just another look at how to use MD solids. It is quite easy, as you know, but doesn't hurt to have another shot at it. And then you're also going to notice down here in number 4, there is a reference to the shaft design procedure handout. I have mine printed out underneath my camera here, and we'll be referencing that, but that's really kind of our step-by-step process. We follow the book, as we did last time, quite closely, but there are some nuances that I've kind of added into the process, I think, to make it a little bit easier to understand, but it kind of fills in some of the blanks that the book doesn't necessarily get to in their procedure. And then there is the spreadsheet here. We did make some changes the last time. If you haven't updated it yet, make sure that you download this version of the spreadsheet because it should be all good again. We shouldn't have those issues that we had last time. We had to take a little bit of a break and straighten some things out. And I think I know it was because of kind of moving things, but so you got to be careful, even me. So so that's what our plan is today. Example number 2. So I am going to start by pulling up the Excel spreadsheet. And I've got it right here. So if you want to do that very same thing, and then I am going to save it as, and I'll browse. I put everything on my desktop, but you can browse and put it wherever you need it to go. And I'm going to call it shaft design, and I'm going to do _12_2. So this is our example 12.2. And I'm just going to say save. And then that way I've got it kind of set up, and I'm not going to go over the top of my master copy, if you would. So what we're going to do is we're going to look at our example first, and then we'll come back to our spreadsheet and then start filling in where we can. I'm going to grab a highlighter out of my bag here real quick so that we can kind of identify some of the elements that are important. So first and foremost, let's look here. We've got a shaft in figure 1213. So we're going to turn the page, and you're going to notice that they have a proposed design here up in 1213A. And this is going to be the shaft that we're going to be designing for the elements that are on here. So you'll notice we have a V-belt sheave, bearing support, a chain sprocket, another bearing support, and we have a spur gear. Okay, so you'll notice that at each one of the critical sections where something is happening, we have a letter identified. So we're going to go along with their scheme here and their proposed geometry. Here you'll notice that we have the bearing and the sheave coming on from the left-hand side. We have the bearing and the gear coming on from the right-hand side. And then this is going to be bored out, and it's going to have actually a retaining ring on either side, on both sides, if you would, at point C here as well. Okay, so that's their proposed geometry at this time. And we're going to determine what those minimum shaft diameters are at each one of those locations, you know, so that we can go ahead with, you know, designing the shaft by figuring out what those numbers need to be. So that's the figure. It receives 110 horsepower. Okay, so this is what's coming in, and it's going to be on point C. Okay, coming in at point C on that chain sprocket. It's on page 525. The gear pair at point E is going to deliver. So E is going to deliver 80 horsepower to an electrical generator. And then the V-belt sheave is going to deliver 30 to a bucket elevator. Okay. Shaft rotates at 1700 RPM. The sprocket, the sheave, and the gear are located axially by retaining rings, as we see in the proposed geometry on the next page. The shaft and the gear are keyed with sled runner key seats, okay? And there is a profile key seat on the sprocket. Use SAE 1040 cold drawn steel. So this is going to be our material for our shaft. And then compute the minimum shaft diameters 1 through 7 at each one of those locations that we're interested in. So now what we're going to do is we're going to get into specifying the material. Now, the spreadsheet, I think, is a place where we can, kind of follow the design once we have things in place. I do want to remind us of, as well, since we're looking at our overview of the shaft design process here, in step number 1, there's that sketch of the overall layout of the shaft. So the book kind of did that for us already, okay? For your designs that you're going to do for the full shaft design, for the homework, you're going to have to kind of come up with that. You're going to have to come up with that. I shouldn't say kind of. You're going to have to come up with that. Additionally, when we do our gearbox design, you'll be coming up with a scheme as well. Okay, so if you want to look at the examples that we've done, get some ideas, talk it through with me, propose something, that's totally fine, or Ryan, and we can give you some input on that if you need it. Okay, so knowing where gear, belts, and chain drive locations are, bearing locations, retaining rings, shoulders, keys, and then the dimensions on center for each one of those elements are going to be essential. So that's kind of like, that's background that's done for us already in this problem. Then number 2 here, this is when we're going to be putting in our material. Now, for example, 12.1, we kind of went through that process. We're going to do that very same thing now for example 2 for a different material. Okay, a different material. They're calling out 1040 SAE cold drawn steel. So I'm going to go back to my my spreadsheet here, and on sheet 1, the very top, I'm just going to fill in the call out SAE 1040 cold drawn STL, cold drawn steel. And we need to now put in our yield strength for that shaft material. So we're going to go to the back of our book, Appendix 3 and possibly 4. We saw last time we looked up for Appendix 3 for the material that was there. It wasn't specifically there, so we had to look at an actual diagram. But let's check with Appendix 3 first to see if we can find SAE 1040. So back underneath here, you're just going to go to the back of the book, and we are going to find Appendix 3. Appendix 3 starts on page 787. And you're going to notice that down that first column, 1040, cold drawn steel is on that chart for us. So we can use this chart then to get the information that we need. So over on the right-hand side, you kind of keep going over. Yield strength is going to be the SY that we need. And then the tensile strength is the ultimate strength as well. So it's going to be 80. So 71,080. You're going to notice in the book, they found those same 2 numbers right there as well. So we're going to input those into our spreadsheet. So the yield strength is going to be 71,000 and 80,000 for our ultimate strength. Our endurance strength, you're going to notice here on the right-hand side, it says, and now this is the 6th edition, so read the red. If you do have the 5th edition, I kind of have kept these hanging around in there because if you don't want to pay the full price of the most current version, there are used versions out there that are going to be less expensive of the 5th edition. So I have those references here as well. But I am working out of the 6th edition. So this is going to be on page 179, and we're going to look at figure 511. Another one here. So 179. Now, something that I've noticed as a comment that comes in more often than you would think is that, especially when we're working with like vendor catalogs or even out of the book here, there's a lot of charts to read. Okay, there's a lot of charts to read. And I'm going to tell you, that's kind of going to be your life when you're out designing, especially when you're incorporating vendor information into what you're doing. It's really kind of getting used to, and every vendor is going to have their stuff set up a little differently. So so it's good to get that experience here, but yeah, it's kind of a lot sometimes. So here's another chart that we get to read. So what we're going to find here is going to be our tensile strength, or remember, that's our ultimate strength, SU. So it's really the same name, for both. So, so we had 80,000. So we're going to find 80 over here, and we're going to go up that line until we get to the machined, assuming that we're machining this. And then we're going to read that over. Okay. And I'm just going to take a peek at what they came up with. I think they came up with 30,000. They did. Right there's 30,000 for their endurance strength. Okay. So we will put in our spreadsheet 30,000. Now, the next one is going to be our reliability factor. Now, here as well, you're going to notice that we're going to find that on page 181 on table 5.3, and then also the size factor. Now, before we go there, it's worth looking underneath here, because remember, they're kind of guiding us in this example, and they're kind of the experience, if you would. And those two are kind of relative, number one, to the industry that you're in reliability wise. And number two, with a little bit of experience, you kind of know like what the sizes of the shafts that you're expecting. And that's what that second table is all about, the size factor. So they came up with a size factor of 0.85, and their reliability factor is 0.81. But let's go to page 181 and look at what that means. So as far as the reliability factor, this is looking down that first column, and they're using CR equal to 0.81. They're expecting a reliability of 99%. Okay. If you want to go up higher, wouldn't be unreasonable. You could use the 0.75 then, but they kept it at 0.81. And then as far as the size factor, the size factor is right here. Okay. And if we go up a little bit and find, they said 0.85. So right between here and here, right? Over and down. So they're expecting their diameters to be between 1 and 2 inches. Okay. And again, as you gain experience, or as you're, working someplace, you would probably have an idea of where you would expect things to land. And then you would go up and over for that CS factor. So we'll use what they chose, which is the 0.85. And we're going to put those two factors into our spreadsheet. So for the CR factor, 0.81, for the size factor, 0.85. And then once we have those two in, it calculates for us the modified endurance strength. That modified endurance strength then is going to be used, and also the yield strength on our sheet 2. You don't have to go there yet, but you're going to notice that these values are populated for us already in green. We don't have to fill those in. Okay. So, so that's what this kind of feeds, if you would. Let's get back to our process and see where we're at. What was that? In sheet 2, you're going to notice that modified endurance strength, yield strength is going to be filled in. And that's why you got to be careful when you're moving things around in that second sheet, because it could, not grab the right area from the first sheet. So you always want to check those. I've had firsthand experience at that. All right. So, so let's go back underneath, kind of catch ourselves up on our process. Okay. So, so we looked at our layout. We've determined our materials. Okay. Oh, was there? I'm sorry.
Yeah, I had a quick question on the size factor chart.
Yeah. Yeah. What's up?
And
Go
just
ahead, Eric.
where the book's getting their number from.
What was that?
I don't really get where the book's getting their number from on the size factor chart.
Okay, so that was on page 181. So you'll notice here, at this point, when we're this early in the shaft design process, we really don't know what the final numbers are going to be. Okay, so they came up with, they got a 0.85 is what they chose. So right about here. And if you go down, what that tells me is they're expecting their diameters to be between 1 and 2 inches. You as a designer would have probably an idea, with some experience, like looking at other places on a machine that you might be designing for, or an element or a product. You might have more insights on where you would fall on this chart. And then what you would do is you would find where you would expect yourself to be. This is an estimate. This is not like science here. We're going to go straight up and over, and that's what that number is. Okay. Yeah. Well, yes and no. I kind of with what I explained. With some experience, you're not going to know at this point what it's exactly going to be, but it's a factor that we need to put in there to adjust that endurance strength to kind of move it up. So if you expect, for instance, to be larger values, then this is going to be your value for your CR factor. And then if it's not as large, then you're going to be over here. And I believe that's a divide into that modified endurance strength. So the larger that you get, it's going to push that endurance strength up further that you need to have. Okay. So yeah, it's just one of the things that we have to put in there. Does that answer it, Eric?
Not really, but I guess I'm not sure how
It's
we're
called a
supposed to
design
know.
process. We don't always have all the answers figured out beforehand. And all that this does is they're estimating where they think their diameters are going to be. That's what it is.
Is this going to be like given on our homework
Nope.
or?
Nope. You're going to have to put it in.
All right.
Yep. And so you're going to take a guess at that point because you don't have a lot of experience with it yet. Okay. So in the first problem we had, I think it was in example 1, their CS was 0.75. Okay. In this one, they're picking 0.85. So it means that the other ones, they were expecting a little bit larger diameters. And in this one, they're expecting a little bit smaller. Okay. Now, let's say you go through and you pick 0.75 that you thought it was going to be about 1 inch. And then you go through and you're like, ooh, these are actually coming out to be like 5 inches. Then go ahead, go and adjust. And that's what the beauty of the spreadsheet. You can go back and you can adjust your endurance strength so that you can then more accurately reflect it in your calculations and see how it affects your diameters. Does that make sense? Design isn't a straight line. Design isn't something you're going to know all the answers at the beginning. And it's just a factor we need to use to kind of estimate what do we anticipate that endurance strength to be. Okay. All right. Okay, so let's get, oh, I know I was looking underneath here. So as we look, we did our material. And now the next place we're going to go is we're going to be determining the torque on the shaft. Okay, so we need to look back to our problem statement. And you're going to notice that what's coming in here is 110 horsepower on our chain sprocket right here. Okay. And then it's going to deliver 30 over and out of our V-belt. And then it's going to deliver on the other side, 80 horsepower to our spur gear. Okay. So our input is going to be on C, which is our chain sprocket. And then one of the outputs is going to be at A and one is going to be at E. So we're going to use these letters on the next part of the spreadsheet. So horsepower, we know that there's 110 coming in, 1700 RPMs. So we're going to put those in there. And this is going to be just on point C. C is going to see that maximum amount. Okay. And that's our chain sprocket. The next one we're going to put in is the 30 horsepower, 1700 RPMs. And this is going to go from C to A, which was the belt drive, the V-belt shift. Okay, there we go. And then the last one that we have is going to be 80 horsepower, 1700 RPMs. And this one is going to go from C to E. Oopsie. E. Okay. So these are the separate torques that we're going to see. This torque right here, the 4076, is going to be when we are looking at point C. And we're going to be needing that to determine what are the forces that chain sprocket is going to then exert on the shaft at that point. The next one here is going to be the V-belt shiv. And it's going to be from C to A. So we'll look at the torque diagram in just a second. And then you're going to notice that the last one here is 2964. That one's going to go out on the gear that's on the right end, which is point E. So if we go back underneath here, you're going to notice that we'll create a torque diagram in a little bit, but you see that this maximum amount right here, the 4,076 is over C. And then down here, 1,112 torque, the 30 horsepower is going out at A. And then the 80, which is 2965 pound-inches of torque, is going out on the center of E. Okay. So we're not going to do a torque diagram just yet, but those are the values that we need. Okay. Now, the next thing that we're going to do, so that's on the spreadsheet. The next thing we're going to do is determine the forces on the shaft generated by the gears, the chain drive, the chain sprocket, and the V-belt sheave. Okay. So let's go back to our spreadsheet. And this is familiar to us. We looked at gear forces the last time we were together, but if we go down a little bit further, you're going to notice that there's a place for chain sprocket forces and for V-belt sheave forces. Okay. So let's start where, we're normally used to. Let's do the gear forces. So the gear forces, it's asking us to put our torque in first. So we need to go back and look at where the gear is. The gear is point E here. And point E, we know from C to E, is going to be the 2965. And it's also the amount that 2965, yep, is the amount that we have here from C to E. So because the gear is at E, we're going to use this value of 29. You can put in 65 if you want to round it, or it's right there, 2964.71 is going to be my value, and that's from above. The diameter of the gear. So the gear has been picked out for us. And you'll notice that up in this illustration, it says that it's a 12-inch diameter, or pitch diameter. So I'm going to go back over here, 12 inches. And then the pressure angle is going to be 20, and that's going to give us our radial force. So this is our tangential and our radial force magnitudes. Okay. As we go down a little bit further, there's only one gear on the shaft, so we only have to do one of those this time. Then we're going to have our chain sprocket force, okay? So if we go back underneath here, our chain sprocket is found at point C, okay? And as we said earlier, we know that at point C, this is seeing all the torque, so it's based on the 110 power coming in, going at 1,700 RPMs. So the torque here at C, and I'm gonna put this location is at C. This torque is 4,076. There we go. And the diameter of that sprocket is 10 inches from the diagram. So now it has put in here for us the bending force. Okay, it's put in here for the bending force, and this is the single bending force. So if this would be vertical or horizontal, this would be the one number that we would put on the shaft. But, but you will notice that in the illustration up here, the chain is coming in at an angle. Okay, it's not horizontal or vertical. So we need to determine the X and Y components of that force. So this force, if you would be pulling away, okay, right along the center there. But because we are at 40-degree angle, we're going to have an X component and we're going to have a Y component. Okay. Sound like statics? I hope. I didn't have you guys. Next year I get to be like, sounds like statics, right? Because I would have had all of them. What was that? Oh, good. Then you're seeing another application. So, so as we look here, now what we need to do is figure out those X and Y's, but our spreadsheet will help us with that. So angle of orientation, you're going to notice we have another value to fill in here. If it's applicable, if this is vertical or horizontal, then you just use that value of 815 and put it in the orientation. But because this is at an angle, unless you want to do the components by yourself. I mean, it's easy, it's not hard. We're going to put in now, we're going to measure this angle from our standard 0 in a counterclockwise direction. So looking down, if this is 0 and we go counterclockwise around, that would be 270 minus 40 would be 230 degrees. You guys see that? Okay. So we're going to go back and we're going to put in 230 right there. And now you'll notice that it gives us our X and Y values. If these would be positive values, they're not. Positive means that it's going to be pointing to the right in the X and it would be pointing up in the Y. But because they're negative, they're just going to be opposite that, right? Okay, so it gives us our directions. So that's the chain sprocket. Any questions on that one? So that one's a little bit different than the gears that we've been doing.
How you got the 2, 3 again? You guys see how you physically, how do you find the starting point from go off of that?
Your standard 0 degrees,
Oh.
horizontal. Yep, standard 0. So then you're going to go counterclockwise from that. Bless you.
So why that? Why?
Because this angle right here is 40 from 270.
Yeah.
So this would be 270 minus 40, and you have your 30-degree angle right here. Because this is where the belt is coming, or I'm sorry, the chain. That's what these lines are. So the chain, there would be another sprocket down here, and that's going to be the direction. And then the actual chain force would be in the middle here, going down and to the left. So that's how we get the X and Y, the X and Y.
I just wasn't sure.
Yeah.
What 40
Yep. 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 So it's just saying from vertical or the 270. Any other questions? Okay, because this one's a little bit different, not hard, but a little different. All right. Then the last one that we need to do is going to be our V-belt sheave. So if we go back over here, we're going to notice the V-belt sheave is on the end right here, and it is going up and to the left. So there would be another V-belt here. And so its force is going to go like on center this way. Okay. Up and to the left. But because it's at an angle again, we're going to have to determine what its components are. So first things first, you'll notice that this is a 6-inch V-belt sheave. So I'm going to go back over here. My torque at the V-belt, that's A, right? So my torque at A was 11. They're using 1112. So 1,112. That's about what ours is. I mean, if you round up. So 1112. Okay. And the sheave location is going to be at point A. And then the pitch diameter given in that design proposal is 6 inches. So this would be the bending force that would be created on center. And then we're going to add in our angle. So if we look at the angle here, the angle that we're given this time is 60 degrees from here. So if we look here, that would be 60 degrees here as well, right? So from our standard 0 degrees here, we would go counterclockwise. It would be 180 minus 60 or 120. You know, and then they're giving us the directions of the forces. So notice here, your X force is going to be negative 178. That means it's pointing to the left. And then we have a positive for that Y, which makes sense. It's going to be pointing up. So if we look back over here, the components of this would have the Y pointing up and the X would be going to the left. Okay. All right. Now, those are the 3 elements that are on our shaft. We did the forces for the V-belt, sprocket, and the gear. Okay, we don't need to do any forces right now. We'll get these for the bearings. Those are going to be reactions of the supports that MD Solids is going to help us with. Okay, so so questions so far? Now, just out of kind of courtesy, I'm going to stop the recording here to kind of, you know, put this at like our input values for sheet 1. I'm going to start a new spread or new recording that's then going to continue with the process, just so it's not so hard to try to sift through if you need to go back and reference anything. So I'm just going to stop here for a second and we will be back.